I was just finishing up a snack. Colin, good to see you. Just got mentioned in an email. Ryan Farley just mentioned you. Dr. Farley, I should say. Ay. Grabbing snack, getting ready. Good to see you, Colin. The new name cracks me up. Hair's just getting crazy these days. Oh, man. Waking up. I need some energy. How's everyone doing? Megan, good to see you there. Grace, good to see you there. Louie, good to see you there. Zariah, good to see you there. We're going to jump into doing some of the assignment. What should we do first? The Canvas content, or should we do Chapter 12 homework quiz? What should we do? Yeah. How did you figure out the probability was... I just made that up. I'll go, let's show that. From class. Homework and quiz. And here we go. Let's see. Homework or Canvas content. We will take the vote. We'll probably got enough time for vote. Both. Let me pull up Pearson while we talk. Yeah, I just made it up. I was just like, here's the probabilities. And I messed it up. Yeah. Like, I'll make this up. Yeah, I just made it up. Like, there's the... I love coding. Coding is fun. People say it's not fun. I say it's fun. Why can't it be both for some people? Let's see. The vote is going for the homework. Looks like we're doing the homework. Chapter 12 homework. When is Chapter 12 homework due? 7 votes. Good to see everyone here. Let me save what we did in our class video. There's the class video saved. Go over to office hours video. Today. Is there a list of vocab we need to study? The test 2 review kind of has it. I think the review videos, Tristan, good questions, Tristan, right there. I like that. Let me throw you some points. The review videos have a lot, and also the playlists. So if you go here to the review page, you will see we've got the exam 2 practice test, the exam 2 key, the formula sheet, which know this inside and out, know what everything means on here, regression equation, residual equation, rules for probability, and chapter 13 equations. And can we go back? And then the topics right here, I do go through these in the review videos, but you can see a lot of the terms and stuff throughout here, especially this is a heavy term chapter right here. Does that help out, Tristan, right there? What I would do is I would watch, I don't know how far back this video goes on sampling. It's not showing the playlist. The sampling video has like 2016 election in it or so. Check it out. I use a Simpsons image from it. But you can see I do interpretations. You can also see videos down here. So check this out. Here, we'll put this as a note for this. Reviewing for the test. So reviewing for test 2. Okay. And so now let's hop over here and talk about some Pearson. So we're going to do the full homework. When is the homework due? The 24th. Is that today? Today? Oh my gosh. Oh, the homework's only 5 questions. Really? Okay. So let's get the homework done. Who's here to get the homework done? Say hello in the chat if you're here to get the homework done. So 523. Stat 201. Hello. Stat 201, Chapter 12 homework. What's up? Oh my gosh, so good to see everyone here. Good to see you, Jesse and Hannah and Zariah and Tristan and Anya and Grace and Louie and Mubot. Always good to see Mubot.
Thank you, Brian. Really took a long time for you to put me on screen, though.
It was worth it, Mubot. It was worth it. Chapter 12 homework, question 1. Let's do this. First one I think is about Anya. Tell me if that's right there. Thank you. 5,000 points. Appreciate it. Anya. Anya. Appreciate it. Want to make sure I get it right. So with this, Unaya, like Nye. Unaya, like Bill Nye. Unaya. Okay. Yes. Unaya. Okay, good. Like Bill. Okay, yeah. Anaya. I got it. Thank you so much. Woohoo! Thank you so much. Oh man. I'm not even kidding. I've probably said this before. I literally have a reading disability, and I think I get anxiety too. Uh, I do want to make sure everyone knows I really want to make sure I get those things right. It causes me anxiety sometimes. Anyways, we got that, and thank you so much. Let's do this. Let's ace this. Let's ace this homework. I have flipped heads 5 times in a row. The next one has to be tails. What fallacy is this? We talked about this in class. What fallacy is this? What fallacy is this? What fallacy is this? Who knows? I've flipped it 5 times in a row. Law of averages, gambler's fallacy. So really right here, for the outcome to be truly random, the friend should not make any predictions. There's no law of averages for the short run. The first 5 flips do not affect the 6th. That talks about independence. So this is each coin flip is independent. Good to see you there, Brianna. Each flip is independent. Thank you so much right there. Each coin flip is independent of the previous. So then to think that they would impact would be the law of averages or gambler's fallacy, but there is no law of averages. And you see it right there. There's no such thing as like I'm due for a tails flip. Okay, 1 question down. Let's get the next one here. Now, here's the thing. Whenever you encounter a question like this, do not click the drop-down box. I know you want to, but you do better and you understand these things better when you can answer it without the drop-down. The property that states for independent trials as the number of trials increases, the long-run relative frequency of an outcome gets closer to the true probability that it's that graph we saw that goes like this, that says the larger the number of trials, but not exactly trials and what it's called. What is this called? This is called the what? As you increase the number of trials, you're more likely to see the true probability of an event. Look at your notes. This one's real. This is not a fallacy. What is this called? As you increase the number of trials, you're more likely to see the true probability of an event. The law of large numbers, exactly. Sorry, my contact's acting up. I'm fixing it real quick. Hence the pause. The law of large numbers, and you can see it right here. What it means is if you walk down and you see a traffic light, and that traffic light is green, well, the first time you saw it, you might think 100% probability that that traffic light is green because you've only seen it one time and it was green every time. But as you increase the number of trials, i.e. more trials, you're going to see the true probability of that traffic light being green, and the overall probability can be estimated by a large number of trials. That's what we mean by numbers, law of large numbers. Numbers means the trials. So that's when you hear law of large numbers. The numbers means the number of trials you are doing. So after a long amount of trials, it starts to stabilize around the value that's probably the truth. Now, of course, these need to be independent random trials that you're not just walking down at a certain time, but that would be the law of large numbers. Empirical probability is more like the 68, 95, 99%, not used here. Sample space is everything that could occur. Law of averages is a fallacy saying something is due for a win. Okay, we already got a 40 on this. Okay, we're gonna have this done in a moment. To help people come to office hours, just get it done. That's what I've heard people say. Just come to office hours. You get it done. We get it done quick. Do it now. Okay. This question is a little bit wordy. Let's break it down. Whenever you're doing a probability question, I suggest writing out the sample space of everything that can occur. So we're going to break this question down into 2 things that could occur. Someone either has no landline or they have a landline. Does that make sense? What is the probability someone does not have, for my question, what is the probability they do not have a landline? So read my question right here. And what is the probability they do not have a landline? What is the probability they do not have a landline? Because you either have a landline. If you're wondering what a landline is, it's when you pick up the phone and it's on a cord or it's on a cordless phone. I thought cordless phones were so cool. Be like, I'm just going to take the phone and go over to Mom and Dad. That's how I sounded when I was a kid. It's going to be that. And what we do is we write out a table. And the table is going to be the associated probabilities. I.e., event A is landline. Event B is no landline, or landline no. No landline. And the associated probability of event A is 51%. Now, why, according to the second rule of probability, is this a valid set of probabilities? Why? And great job, Ava, and everyone right there. Great work. Great job. Why is this a valid set of probabilities? Why is that a valid set of probabilities? Who knows? Oh, no. Wait. I'm reversing it. It should be landline is 49%, no landline is 51%. Great job. I like it. People catching my errors right there. Great work, everybody. It's a valid set of it was still a valid set of probabilities, and it was a valid set of probabilities because a valid set of probabilities adds up to 1. So the valid set of probabilities adds up to 1 right there. And so if it adds up to 1, this is a valid probability set. And so that's just a probability set has to add up to 1 if you add up all the probabilities. So this is a valid probability set. I do have to get it right. And now we get into the actual questions. What is the probability that all 4 of these houses have a landline? Now this is where you think the first has a landline and the second has a landline and the third has a landline. What must you assume about these houses? And go to the formula sheet to assume, that might be yours, HCT. That might be yours. And sounds about right. Check your numbers, but that sounds like a way you could be solving it. I think Zariah has it right there. And take a look. To multiply things together, you must assume they are what of each other. To multiply things together, you must have assumed that these houses are all what, which might or might not be true. We're going to assume it for this problem, but you have to assume to multiply things together, and it's a good look at the formula sheet here because you get to bring this to the test. You have to assume that the probabilities are all what? Independent. Great job, Ava. Independent means that if one thing is happening, it does not influence another. So you see it right there. Independent, outcome of one thing does not impact another. So if they are independent, we can use the multiplication word with the word and then we can multiply. And simply, we just turn this into the math. Landline is 49%, so it becomes 49% times 49%. Does everyone see you can write it out as words? What if they weren't? It would require a little bit different of mathematics, and it would be a harder problem that we won't cover in this class. Good questions, Zariah, right there. So we definitely, there are harder problems. There are ways to do dependent probabilities. I think it's that the probability of A times B is equal to the probability of B times the probability of A given B has occurred. And so here's, just really quickly, this is the advanced way. I didn't put a thing around that. If they're independent, then the probability of A would be equal to the probability of A given B has occurred. So that little dash, that slash mark right there means given. So because think about this, if they're independent, given B has occurred would do what to the probability of A? Given B has occurred would not impact A. So the probability of A would be still the same if B had occurred. So this says the probability of A given B has occurred. So the probability of A is equal to the probability of A given B has occurred if it does not change. Don't worry, if that goes too in depth for you, literally the probability of A and B is equal to the probability of A and B times each other because we're assuming they're independent. So don't worry if that. This is the formula sheet for the test. I want to point that out. And whoop, we lost it. The formula sheet for the test shows us that we can multiply together easily when they're just independent. But does that make sense? You would have to do a slightly different equation. You'd have to figure out different sorts of probabilities, but we will not be testing you on that. Good stuff. So it is 0.49, 234, 0.49 to the fourth power. And that is the answer to the first question. 5 decimals. 1, 2, 3, 4, 5. There we go. Now this one, a little tricky right here. You ready? What is the probability? You're welcome. What is the probability that at least one of them does not have a landline? So either, say it with me, think about this. Either every house has a landline or what? So either, and we'll write this down. This is how I solve this. So either all 4 houses have landlines or what? Either all 4, so it's either the case that everybody has a landline, all 4 of these houses, or what? And the or is over here. So it's either the case that all 4 houses have landlines, that's in the yellow, or what? Or what? It's either the case that all 4 have landlines or what? You can see it in the green. Either every house has a landline or what? It could be that none have a landline, but remember, this is an or. It could be the case that none have landlines. So it could be either they all have landlines, but it's not just that none have landlines. And then HCT is seeing it, or at least one doesn't. Does that make sense? Which is what we're trying to figure out in this next problem, is the probability of at least one does not. Does not. Run out of room. So either they all have landlines or at least one does not. Since these are complements, adding them up equals to what? Because it's either the case that this occurs over here or this occurs over here. One of those two things must occur. So what is the probability of that or that? What is the probability over here of both, like either of those? Either this or this. And this is everything that can occur up here. It's either going to be 1, 2, 3, 4, or 0. So the probability is what? Because one of those things must occur. That's the hint. One of these things must occur. One of these things must occur. If one of them must occur, what's the probability of a thing that must happen? Because if you go to... Well, I think you got the answer to the question, HCT. And so this is where... And Megan's got right there. So what we're doing right now, Zariah, is we're writing out the table because we know the probability of this. The first thing, we have it up here, is 0.057 or so. We're just going to write 0.057. And then the other one, and HCT has it right there, is 0.094, because these things are what of each other. We'll just write it like this for now. We're going to carry the decimals, but these two things are what of each other. These two associated probabilities are what of each other. They're complements, exactly, because it's either the case that everyone has a landline or it's not that everyone has a landline. One person, at least one person doesn't. It could be that no one has a landline, one person, 2 people, 3 people. It's everything but everyone has landlines. So you just do 1 minus this. So you literally just go 1 minus probability all have landlines equals probability at least one doesn't. Does not. Does that make sense? How are we doing on this one, Zariah? These are tricky, and I'll be doing some more. So you subtract 1. Exactly. It's just you do 1 minus this right there. Great job. So it's just 1 minus to get the other side of it. That's all it is. It can be tough. Like, the more you do these, the more you get the hang of them. But literally, this question is just 1 minus the first answer. And that's got it. They are complements. There you go. It's going to be that number. What is the probability that at least one of them does have a landline? Was probably so. Now think about this. If we're trying to figure out the probability at least one does have a landline, I want you to see how I'm drawing this table. I'm going to put the line for at least one has a landline over here. So what are my two things? How would you describe event in yellow now? Either this is the case or this is the case. So what are the two cases right here? Because this is how many people have landlines. Describe the event in yellow. So we're doing the next one. So what's the event in yellow? It's either the case what or what? That is right, Ava. So what's the event in yellow? Exactly, HCT. It's either that no one has a landline. So this is no one has. Either no one has a landline or at least one has it. Does that make sense? At least one has. Because this is at least one has, because 1, 2, 3, or 4 could have, or no one has. So you know how would we find the probability no one has a landline? What is the probability of all 4 houses no one has a landline? So now we need to think for 4 houses, the probability no one has a landline. Like the first does not have a landline, not a landline, and not a landline. Exactly, 0.54 to that power. And that's going to be this probability here. So this will be 1 minus 0.54, or 0.51, sorry. 0.51 to the 4th power. What is wrong with me today? Who feels like they get this question? These are tricky. These are just the complements. It's like either this or not this occurs. Like, because this is a valid probability table too. It adds up to 1 because either 0, 1, 2, 3, or 4 people. So you can put a line here and say it's either the case that no one has a landline or at least one person has a landline. And so this is of the 4 houses. So you have to say all 4 houses don't have landlines, or it's the case that at least one of the houses has a landline. So that's got it. That is how we do it. 2, 3, 4. And there's the probability. Little tricky. This is slightly tricky, but it's a good fair one. 1, 2, 3, 4, 5. There we go. Okay, we're almost done with the homework here. So let's see. And please ask questions if you have them. We might even jump to one of these questions in the quiz next. Okay. When my parrot is fed breakfast in the morning, it either screams petulantly, eats it, screams and flings it out of the cage, or it enjoys it. These events are disjoint. Are they independent? You might need help on. Sure, of course, ATT, and tell me what the questions are, and we'll drop them in. So the question is, are these independent? What does independent mean? First, tell me what independent means. I think Anya, wait, Anaya. Please tell me if I got it right. So what does it mean? What does it mean? What does it mean for them to be independent? What does it mean? What does it mean? Exactly, like, and so they would not be independent because they're not independent because they do affect each other. If your parrot eats that thing all happily, then it's not going to fling it out of its cage because it can't do those. So what's interesting is disjoint events are very dependent. It doesn't mean, it's not that dependent or disjoint. It's like, can I be a dude and can I be human? Yeah, if I'm a dude, I'm human. But if you're a human, are you dude? No, not always. And so with that in mind, things that are disjoint must be dependent because if one happens, the other can't. But dependent does not mean disjoint. Like my wife drinking coffee depends on me drinking coffee because if I make coffee, she's more likely to make coffee. But it's not disjoint because we can both drink coffee. Disjoint means if one thing happens, the other can't. And these are disjoint because your parrot can't eat the food happily and toss it out. And because they're disjoint does mean that they are dependent. So are they independent? The answer is no. They are very dependent. Therein kind of explains. Outcome of one does not influence another. Exactly. Last question. I don't like these ones as much. And then what should we do next? Just put homework or put quiz or canvas. I'll do whichever one you want next. Quiz or canvas. What are we going to do next? Drop quiz or canvas in the chat and we will do what you say. If someone doesn't like to watch basketball, the probability quiz. Oh, we got some quiz in the chat. If someone doesn't like to watch basketball, the probability that she will be a football fan is what? So we go here to this table. We've never made a test question that looks like this. It's not a horrible question. So it says, if someone doesn't like to watch basketball, everyone's saying quiz. So they are a no basketball person. They're not rooting for the Vols on Friday. What is the probability that they what? Like football or don't like football? Probability will be a football fan. Oh, cool. Tell me which. So this one right here, we just get the total. There's 59. So it should be 41 out of 59 people. 41 out of 59 people. So 41. I get it right there. Everyone's cracking me up in the chat. So if they are not a basketball fan, the probability they'll be a football fan is 41 out of the 59 people. 41 out of the 59. Here we go. Do we multiply by 100? We'll find out. And it just wants the decimal, I think. So 3 decimals. Hey, we got it. Well, that's it. Okay, let's do the quiz. Let's get some quiz questions done. Let's do some quiz questions. What quiz question do you have? Drop it in the chat. Yeah, I know, right? It's already done. I think we changed it up a little while ago. It used to be, I think, longer, and now it's not. Oh my gosh, look at the M&M ones. Who like the M&M ones? We could do, you know what? Let's do let's do some of the at least one problems. We could do, how about we start with both at least one problems, and we could do like the M&Ms and the blood type problems. Those get people. So drop which questions you have. I'll probably start with these. I know these questions give people trouble, so we're going to start with these questions right here. Please drop your question in the chat. We will try to do it. But I know these ones give people trouble, so we're putting them in the video right now. Chapter 12 quiz for a sales promotion. Okay, so you want to get in the practice of solving problems like the following. You want to draw everything that could occur. When you open up one of those sodas, you either win or what? You either win, you used to look under the cap to see if you won, or what? Good question, ACT. Yeah, if you find some, let me know. I might be able to, I can probably find them too, HTC. Sometimes they're a little hard to find in videos. I've done pretty much everything. There might be like a 10% I've missed. I don't know which ones I've missed, though. And it might be ones that are like, I don't know, like maybe, yeah, good question, ACT. If you find one I've missed, let me know. So you either win or what? We're going to write out our table. So you got to know what to write for the table. You put the table and you write probability of A. You either win or what? And then you have probability of whatever it is A we're talking about. Yeah, let me know. Mm-hmm. And then also message me those. I might find you a video. I'm really good at finding the videos. Sometimes a little hard to find, but I can find them usually. So you either win or what when you buy a soda cap. You might not, the way to describe it, you have to think, is it really that? You either win or what when you get a soda cap? This one's a tough one. You either win or what? Kind of lose, and we might say not win. You either win or you don't win, because you lose. I think win or not win. Lose is fine too. And then the probability you win something is 0.31. Now, what would be the most amazing thing to happen if you bought, let's say, a 6-pack? What would be the coolest thing ever if you bought a 6-pack? If you bought a 6-pack, the coolest thing ever would be what? The coolest thing ever would be what? And each soda is randomly put independent of each other. Win on all 6, so we'd love that. The probability of winning on every single soda is 0.31 to the 6th power. I guess it's 0.31 times 0.31 times 0.31 repeatedly. Win on all 6. But now let's make a table of how you might win. You could win on 0. That's off the screen. You could win on 0, 1, 2, 3, 4, 5, or 6 sodas. Does that make sense? I guess you could put right here the associated event A and the probability of event A below. So what would really be a bummer? Not winning at all. So you either don't win at all, or you what? What is the other side of this? You either don't win at all, or you what? How could you describe the other side of this? You either don't win at all, or what? You either have no winners, or win at least once. Win something. Does that make sense? Who follows me? We've drawn this out now and trying to visualize it. So we can say you either don't win on any of them, or you win at least once. So what this means is we can write the following as an equation. We could write out that 1 is equal to the probability of no wins, or, which is 0 wins, that's this one right there, or the probability of win at least once. We're just kind of shorthanding win at least once, which is that probability. So why not just do this? The probability of win at least once, the probability of win at least once is equal to what? The probability of winning at least once is equal, which is what we want to find. That's what we're trying to look for. The probability of winning at least once is equal to what? What is the probability of winning at least once equal to? The probability of winning at least once is equal to what? The probability of winning at least once is equal to what? Because you've got this equation right here. Well, that's probably that's probably just winning one time. We want to know you buy 6. So you buy 6 sodas. You buy 1, 2, 3, 4, 5, 6, and you want to win at least once. So you're like, man, I hope I win at least once in my 6 sodas. So what's the probability at least one of your sodas is a winner? You got to algebra this. Exactly. 1 and 2, it's Zariah wrote. Great job, Zariah. 1 minus the probability of no wins. And that's because these two things are... well, I don't want to shade... Sorry. This right here. We're just taking everything over here and mathing it to this. Does that make sense, Megan, right there? Because you are either going to have no winners or at least one winners. That's what we drew down here. And then you can just algebra this over by taking this and subtracting it from that side right there. So does that make sense? The probability of winning at least once is everything but no winners. So now we can do equals 1 minus no winners is what? What is the probability of no winners? So all 6 of your sodas are loser. You didn't win, and you didn't win, and you didn't win, and you didn't win. See, I'm saying and you didn't win, and you didn't win. What's the probability of this? What's the probability of no winners? What's the probability of no winners? What's the probability of no winning? You don't win on all 6 of them. The first doesn't win, and the second doesn't win. Exactly. Nice job, Megan. Great work. Great job. Yes, the probability of no winners is all 6 don't win is that. And that's the answer. So whatever the answer is, it's going to be it's probably a smaller number. It's likely you'll win at least once. So 0.23456, 1 minus, and it's about 89%. So we're going to write 0.89 for shorthand there. So it's about 89%. And that means we can solve this one. Now here's the thing. Once you get these down, 3 decimals. So we go right there. Check answer. Good to go. I love these questions because if you know how to do them, you can look. Let me mark this. I'm going to take a guess, and then I'm actually going to solve it. So I want you to walk me through the steps of this. And this is the light bulb. This is another at least one problem. So you purchased, I'm doing them back to back for the at least one. So, yep, light bulb problem. So watch this. You ready? What is the probability that at least one of your light bulbs is defective? So everything but they all work. So 0.204. Oh, God, this is getting small. 3 decimals. Did I get it? I hope. Dang it. It's got to be around here. Is it even closer to this? Is it even... Okay. Well, I was taking guesses and... Oh, wait. Oh, no. 8 times 8, 64. It's 5-pack. 4, 2. Okay, I got a guess now. It's my last guess. That's a serious guess. I was doing wrong. Okay. So the actual answer is going to be, those are all guesses doing it in my head. Yeah, I was pretty far off. And that should be the right answer. There we go. Okay, so how do we get this? I was doing the math wrong in my head, and I was looking at it wrong. And so now let's show how to get this problem. Your light bulb either works or it does not work. This is how to solve these problems. You ready? Every time I write this, I write out the what of all the probabilities. I write out this. I'm looking for a 3-letter word that starts with this. Every time I do these problems, you always see me, and this is great notes to take for yourself, I always write out the what of all the things that could occur. I'm looking for a 3-letter word that starts with this. It always equals to 1 because I'm writing out all the things, the sample space also known as. I'm writing out the what of everything that could occur. So every time I do this, the set, grade HTT, yep, the set of all things that could occur, also known as the sample space, every possible outcome. So it's going to be that your light bulb either works or does not work. Does that make sense? Either light bulb works or does not work, or we could just put not work. And the probability of the light bulb working is going to be 0.78 because the probability it is defective is this. And that's where I flipped in my head. I didn't read the question properly to start. Good to see you, Scout. And so we have either works or does not work. Probability is right there, which is the probability of it does not work, which is this probability down here. The complement of it is the probability it works. Now we're buying a 5-pack. And what we want to see for the 5-pack is what? We're talking about, we'll say these are working light bulbs. In your 5-pack, you'll either have 0, 1, 2, 3, 4, or 5 working light bulbs. This is also an associated event and probability of said event. So if you add up all these things right here, or we should put A up top rather, A and probability of A right there. Because this is now if you buy 5 light bulbs. These are 5 bulbs. And exactly, nice. So we put a line right there and we go like this. Because it's either the case that either they all work, so this would be all work, or at least one defective. At least one not work. So at least one does not work. So the probability they all work would be every single light bulb works, and the probability of working is 0.78 to the 5th power. So then this side of this is just 1 minus. Does it help to fill it out this way? Who feels like, because then this is just the other side. You just do 1 minus, because then it'll add up to 1. So if you add this plus this, it equals 1, the addition of these two things right there. So you just take those right there, because they're just this or this, which is the same thing as this. But you can just get the other side of it. You see, you can just do it down here too. You can just write this probability as 1 minus 0.78. And that's what it is, but you need to solve for it still. But do people feel like this way of solving helps out? That when you write this second table right here, you add the line. I think drawing things out can help out a lot, because either they all work or at least one does not work, which is what we are solving for. At least one is defective is at least one not working. We could have written defective there also. But Zariah and everybody, does this make sense? That's how I found it out. And I did 0.78 to the 5th power by going 0.78 times itself, 3, 4, 5 times itself, not times 5, but 0.78 times 0.78 times 0.78 times 0.78 times 0.78. And then we do 1 minus, and there's the associated probability right there. I really like those problems. I think they're excellent. But so P not working without subtracting, how do we do that? Can you expand, Zariah? Well, you would just use the complement like we're using. Are you saying if you don't use the complement? If you say like if we didn't use the complement, how would we do it? There's some other ways. There's actually really easy ways to solve these. If you want to check your work, here's a binomial applet. Yeah, subtracting is the easiest way. This is the binomial applet. And if you put in here the probability a light bulb works is 78% of the time buying 5 light bulbs, you can see the distribution. And you can figure out 4 or less light bulbs working like this. And there's the probability we just found. So this will actually solve out the problems, the binomial applet I just dropped. Once again, don't, because you could drop it in ChatGPT and it'll tell you the answer too. But this has the associated probabilities, and it's pretty much what we drew out. If you look at the way this is drawn, you can see the more likely and less likely events. And you can also now see the probabilities of 0 light bulbs working, which is virtually impossible. The probability none of them work is 0.22, 2, 3, 4, 5. It's that probability. This is the probability exactly 1 light bulb works, exactly 2, exactly 3, exactly 4. And there's the probability of 5 light bulbs we found by doing 0.78 to the 2, 3, 4, 5th power. So there's that probability right there. Does that make sense, Soraya? Nothing wrong with using this applet. You won't use it on the test, but you can use it to visualize or understand the distribution of all possible things that could occur when it comes to the 5 light bulbs working. And think about this, since there's like a 75% chance, the most likely thing is you'll have like 4 light bulbs working. Could you do the question that talks about the percentage of cars needed to be prepared? Yeah, let's do those car questions. I do. There's 2 versions. Watch this. You ready? I thought I'd get it. Dang it. It's around here somewhere. Round here. We all look the same. Round here, stay up very, 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 very late. And I can't see nothing. Okay, we found it. Okay, let's do the car questions. You're welcome, Zariah. Check out, some guy just recently did a cover of that song. It's really good. Should find his name. Cover's better than Adam Duritz of Counting Crows, if you ask me. So here we go. Consumer repairs. Both questions, both versions. I do like this one a lot. It's pretty fun, pretty easy, and we'll do those M&M problems too. A consumer organization estimates that in a 1-year period, 20% of cars will need to be repaired once, 5% of cars will need to be repaired twice, 1% of car will need 3 or more repairs. So now what did they not tell us right here? Let's write this out as a table. You ready? What did they not tell us? So remember, we're going to take our table, and we have probability of a car. So we have the event A, 1 repair, 2 repair, 3 plus, and the associated probability of this is going to be 20% of the time, or 5% of the time, or 1% of the time. So what did they not give us? They told us the probability a car needs to be repaired once, twice, or 3 or more times. So they did not give us what? And right now, the total probability in the table is 26%. So there's 26% of the probability. No repairs, yep. So no, and that's actually the first question right there. The probability the cars need no repairs is either a car needs some repairs, so this would be known as some repairs, or no repairs. That's some repairs or no repairs. So you can just use words associated with the event A, and we have already figured out the question there, which is no repairs, or rather I should highlight this 0 is the no repairs idea, and the associated probability is going to be this. So there it is. Yes, nice job, Megan. You are correct. The probability that the car will need no more than 1 repair. No more than 1 repair. So tell me what should I encompass? No more than 1 repair should encompass what? What should no more? I should encompass which of these values? If I say I didn't get more than 1 repair last year, that would be what or what repairs? So no more than 1 repairs is going to be what or what? No more than 1 repair. No more than 1 repair. 0, 1. Exactly. Great job, Megan. So that's, you notice how you say 0 or 1? By saying or, you're doing the addition rule right here. And that means they need to be mutually exclusive, which they are. You can't get 0 repairs and also at the same time 1 repair. So you use or, and we would just add these values right here. That's not what I wanted to do. We would add these values right here together and just go right here, and that's going to be 0.94, just adding those together. The probability the car will need some repairs, so that we already did this one. Some repairs is going to be this, and we already found associated probability, and there we go right there. So 94, 26, 74. So 94. I think it was 76. Doing it by memory. 24. I think that should do it for that one. Oh, what did I do? What did I do? 20. Oh, I got the 4s and the 6s reversed. Got the 4s and the 6s. Stay from a region. Yeah, we'll do it next year. I got the. No, I don't know my 6, 7. Sorry, I'll stop. Okay, so here's the other version of it. This one's a little trickier because it's about multiple cars. So once again, and this is it can't be negative. Good question, Grace, right there. Probabilities can't be negative. Number 1 rule: probability. Probabilities range between 0 and 1. Can't be negative. Grace, 5,000 points right there. Good question. It would just be 0.74. The probability your car needs no repairs is 74% of the time. Probability you need some repairs is 26% of the time. The probability of 0 or 1 repairs, which is no more than 1 repairs, is 94% of the time. And so this question is very similar, but it has 2 cars are better than 1. So With this problem, we're going to draw out the same probability table and then use it in a slightly different way. A key problem with this problem, is that it assumes your two cars are independent because we will be using the multiplication rule. The probability of the repairs this time are one repair is going to be 17%, and two repairs is going to be 9%, three repairs is going to be 3%, and then we can do the remaining is, I believe, 71%. You add this up and you get 29%. And we actually break the table apart into this now because you could redefine your table in the following way. You either have no repairs or some repairs. So does this make sense? You either repair your car, so this is repair to some degree, or no repairs. Put a yes if you follow me in the chat. So all of these things over here are defined as the some degree of repair was done to the car. 29% probability one of these things occurs. And this is no repair. Wasn't given. You have to subtract from one. Ava Caesar right there. Great work. This is key to this problem. Once you find out these associated probabilities, you know the probability of no repair, which is good. And you know the probability of repair, which is bad. You are trying to find out these associated probabilities. Then we can start to think about what the question really asks. In this question, it says you have two cars. What is the probability neither will need repair? So when it comes down to it, here's the thing that could occur. Both your cars need repairs. The first need repairs. The second or don't need repairs. This is the new set of everything that could occur. So these are all the things that could occur. Does anyone follow me on this? Like, you can think of this. Can I draw up here? Yes, I can. As everything that could occur. So who follows what I've drawn here? What does this mean down here on the bottom? What does this bottom row mean? Grace is starting to see it. Good. What does this bottom row mean? It's the outcome of what? We could put a word right there. Both cars needed repairs. So what's the probability that both cars will need repairs? We'll look at their questions here in a moment. What's the probability that both your cars need repairs? Use the associated color coding and probabilities to figure out the probability both cars need repairs. It'd be that your first car needed repairs and your second car needed repairs. What's the probability, which is not the first question, but we're just filling out the table. What's the probability they both need repairs? Exactly. So that turns into 0.29 to the second power because it's 0.29 times 0.29. So the probability neither need repair is 0.71 to the second power. You know what you can actually do right here? 0.71 times 0.29 and 0.29 times 0.71. Do you see we're just taking the probability. Whenever you see needs repair, you just put in 0.29. I'm going to erase this. Or maybe I'll zoom in and that might... I don't know if I can zoom in on that area really well. But you just take the associated probability of whatever you're talking about. Like this is why it's squared. And then this is that one there. Maybe I'll just color code it for a second. Should I leave this color coding or remove it? What do people think? Leave the color coding or remove it? Just type leave or remove and I'll do as you say. Does that help seeing it that way? Actually, I think it might. I'll do what you say. If you say take it out, remove it. But that's the associated probabilities. Like we just found all the probabilities for the whole problem. So I might keep it there and I won't say anything yet. So now it says, what is the probability that neither car will need repairs? Well, neither car needing repairs is this one. So that's the answer right there is that one. Neither car need repairs. What's the probability that they will both need repairs? The probability that they will both need repairs, we'll go with a more divergent color, is this one right here. What's the probability that at least one car will need repairs? Should I put it at line, which line should I do? Which line is at least one car needs repairs? Would it be dividing here, here, or here? Line 1, 2, or 3. And if I go below it, it would be at least one car needs repairs. Line 1, 2, or 3. At least one car needs repairs. At least one car needs repairs. At least one car needs repairs. Exactly. Great job, Megan. Because then it's either that they're both fine or at least one car needs repairs. So the math for this is simply going to be 1 minus 0.71 to the second power. And that's the answer there because it's the complement. Does that make sense? So we've just found the answer to every question. They are pointed at it. 0.71 to the second power is the first. 0.29 to the second power is that one. So there we go. So 0.71 times itself is the first one. And then that's also the complement of this is the last one. And then 0.29 is this one. That should do it. There we go. That's got it. Try to draw these things out. This problem is a little tricky because it's talking about two cars, and that's got it. And then people want to do the study from a region left-handed. Oh, yeah, I think it's a good one. Oh, I don't think it's this. This is the M&M Red Cross stuff. Yeah, it's towards the end of it. Oh, here we go. Oh, my gosh. Text is so big over here now. What other questions do you have? Do you want to do the M&M ones? What other questions do people have? I think we did the Canvas content, right? Did we do the Canvas content? Hence why not everyone's asking about it. Everyone's like, I got that. I got Canvas content done. And maybe my vision just got worse over the weekend. Possible. So M&Ms, we'll do the M&Ms one. Thomas, you got it. So a study from a region and suggested that about 27% of people in that region have red hair. It could be left-handed, whatever. Rock nose. It doesn't matter. Blood pressure. Cool. The multiplication rule would suggest that we can multiply this to find out the probability that a brother and sister both have red hair. What's wrong with this reasoning? So, I have hazel eyes. I have green eyes. Do you think my sister is more or less likely to have green eyes? I should say my brother. Do you think it's fine whichever one I say, but I'll tell you why. I have green eyes. Do you think my brother or sister are more or less likely to have green eyes? I think I heard recently green eyes are like one of the least common. I thought blue was. What would you think? Now, there's a key follow-up here that we got to review because do you think my brother or sisters are more or less likely to have green eyes because I have green eyes? Knowing Brian has green eyes, would that mean his brothers and sisters are more or less likely? More, exactly, Louis. So that means the color of my eyes are what from my brother and sister's eye colors? They are what? What word would you say on this screen within this area? What word would you say? The Brian's eye color is not what, or is what of his brother and sister's eye colors? His eye color is what? His eye color is what? Dependent, dependent to some degree. Now, my brother has blue eyes and my sister has green eyes. So it's not like you will know the color of my sibling's eyes, but it's more likely it would influence in some way or at least be related to. Like knowing Brian has green eyes would mean people in his family are more likely to have green eyes. So they're not independent because if one thing happens, it influences the probability of another. Remember what the rule of what independence means? We got it written over here too. Independence means outcome of one thing does not impact another to the degree of would not change what you think about the probability. Make sure to write down these definitions, no examples. Everyone gets stumped on them. I'm like, no. So you can't multiply. The reasoning is wrong. You can't multiply because they're not independent. So where does it say they're not independent? Just, all I read was not independent, and I just clicked that answer. I was like, not independent? That sounds right to me. The Mars Candy Company one. Let's do the Mars Candy Company. That is a longer one. It's a good one. The bowling one's good too. Here we go. Here's the Mars. The Red Cross one's very similar. So, and drop some more questions. We've got time for a few more, y'all. Man, I need that caffeine. I got a bad caffeine addiction. So much caffeine I need. Brian runs off Dunkin'. I haven't had Dunkin' in years. Wouldn't mind it. Okay. 55, 53. What the heck? Bolded what I wrote. Never seen that. Okay, the Red Cross question. Oh, this is the Mars. Okay, so for this one right here, it has two parts, an easy part and a harder part. The easy part right here is pretty much easy. Everyone gets the easy part done so quickly. But the key to this question is writing out the set of all things. Tell me to start out, just so I know you're following along, what letter am I going to write over here on the left? What letter is Brian going to write over here on the left? What letter do I write right there, meaning the outcome or the event we're looking at? A. Great job, Louis, right there. We're going to write A, and this is what you want to do. Grab some crash sheet of paper, do what I'm doing. I think I've learned these things so well because I've been doing this for decades. I've been writing these things down. Great job, Brianna, right there. Going to write down A and the probability of A. A just means whatever we're thinking about. You could write whatever you want. Win, lose, draw. You know it. And then go right here and write probability of A. And then we're going to write down the events. So the events are yellow. And then we have red. And then we have orange. We have blue. And then we have green. And then we have brown. I'm going to do brown as BN. And green took up too much room, and brown will be BN right there. So, because brown and blue are very close in the color, like blue, BL, brown's BR. Blue, brown. I'll learn how to spell. So with this in mind right here, the probability of yellow is going to be 20%. It just says it. Probability of red is 20%. The probability of orange, blue, and green is 10% everything. And now, to be a valid probability table, this table must add up to what? Currently, the table, when you add it up, adds up to 70, I believe. Correct me if I'm wrong. Currently adds up to 70, but the table must add up to what to be a valid probability set of everything that can occur? The probability of the set of everything, that's where you write probability of set, must add up to 1. So then this has to be 30% to complete the valid probability table. So now we have a valid probability table, and we can work on the associated problem. Let's drop it over here on the side and start to look at the problem. So we'll zoom in. Okay, I need to go away when I make this appear. So the first question asks, what is the probability the M&M is yellow? Are they really just going there? The probability that the M&M is yellow is 20%. We just look at our table. What is the probability it's green or red? So when you do the probability it's green or red, you're going to add together the two probabilities, green or red. Remember, it's saying or right here. Look at our sheet. When you do this on the sheet and you do or, they have to be disjoint. It can't be green or red at the same time. Mutually exclusive means both can't happen at the same time. And so then it's just a 30% probability. What is the probability it's not brown? Who can solve this one? I'm going to throw this one to the class real quick. What's the probability it's not brown? Not brown. Not brown. And that is the complement rule. This is the complement rule. Complement rule is everything but that thing. So what is the probability it's not brown? What is the probability it's not brown? So there's the complement. You just do 1 minus. So it's probability it's not brown. Great job, Ava, right there. It's going to be 0.7. What is the probability it's spotted? Not in the table. That's a lie. Now we get to the harder part of the problem where people get stuck. It says we are selecting 3 M&Ms. So we're going to go over here and take 3 random M&Ms from the bag, M&M1, M&M2, M&M3, and we're going to look at these possibilities. The probability that you picked 3 yellow M&Ms. So what's the probability the first is yellow, and the second is yellow, and the third is yellow? Notice I'm saying and. So we're saying what's the probability all 3 are yellow? The first is yellow, and the second is yellow, and the third is yellow. What's the probability? And notice I said and. What's the probability the first is yellow, and the second is yellow, and third is yellow? And we're going to pretend that each M&M is independent of the previous. What's the probability? What is the associated probability that all the M&Ms are yellow? First is yellow, and the second is yellow, and the third is yellow. I have this question 4. Yeah, it'd be 0, correct. There's no spotted M&Ms. What's the probability the first is yellow, and the second is yellow, and the third is yellow? Unfortunately, each question is its own, is part of the quiz. Sorry, HCT. If there's a decimal error, let me know. Well, the probability an M&M is yellow is this, and then the probability we draw 3 in a row is just going to be multiplying 3 times. Now, this one's where people get stuck. They say, how in the world can I get the probability the first one, I hoped I wouldn't do that, the probability of the third one being the first blue one? Okay, So if the third one was the first blue, then what do you know about the other M&Ms? If the third one was the first blue, then what do you know about the other ones? If the third one was the first blue, the other M&Ms were what? If the third one was the first blue, yeah, I can fix ACT. Message me on it, email, and I'll fix it. If the third one was the first blue, then the other ones were what? The first one was what, and the second one was what? And maybe we'll put the math over here on the side. We'll write the math. So this is the visual. This is the math of it. So I'm going to multiply. If the third one is the first blue, then the other ones were what? Think if the third one's the first blue, then these other ones have to be what? Not what? If the third one is the first blue, then the first one was what, and the second one was what? Don't think about not blue. Exactly. So we got here not blue times not blue times blue, and so the probability of not blue is that not blue, and I keep erasing because I'm pressing the pen, and then probability of blue. So this is going to be like 0.081, 0.0081, I think. 0.0081. Hopefully I'm not doing any wrong decimals. Okay, so the next one says the probability that none are green. The probability that none are green, that's easy. Well, the probability that none are green is just going to be the first is not green, and the second is not green, and the third is not green. So what's the probability of getting a not green M&M? Because what we're going to say right here is we would have to say the first was not green, not green, not green. So what's the probability of a not green M&M? Here's green. What's the probability of a not green? So we would say, well, we have to get a not green, not green, not green. So what's the probability of not green? You're drawing 3 M&Ms. What's the probability all 3 are not green? Silence. That's going to be... Yep, Ava, great work. Yep. There we go. The probability at least one brown M&M. So this is the tricky one, I'd say. Let me fix up the visual. There's going to be more room. So at least one brown. So this is like the first problems we did with the soda pops and also the light bulb problems. So you're going to make a table right here. If you want to do at least one brown, then there's 0 brown, 1 brown, 2 brown, or 3 brown M&Ms. So you either have no brown M&Ms or at least one. At least one. Because it could be 1, 2, or 3. The probability of no brown M&Ms would be, remember brown is a 30% probability, so it'd be 0.70 to the third. Because the first was not brown, and the second was not brown, and the third was not brown. So the probability of no brown M&Ms is this. So the other side of the table is simply 1 minus this. Does that make sense? We did a few of these earlier, but these two sides have to add up to 1, and if you do the complement, they add up to 1. So you're either going to have no brown M&Ms. Probability of brown M&Ms is 30%. So the first is not brown, and the second is not brown, and the third is not brown is 0.7 times 0.7 times 0.7. And that gets the associated probability of no brown M&Ms, and then at least one brown M&Ms is the other side of the table. Hopefully, it's a tricky one. Should do it. What? Where did we make an error? Where did we make an error? Was it this one? It's the easiest one to check. I feel like we did that one right. Now my computer's going to crash. Round to the... Do not round. Round none of these. What is it doing now? No! Who sees the error? I will throw some big points if we see the error. The probability of it... Wait, at least one brown M&M. We did that. We did the other side of it. None are green. Probability. Did I mess up the green? I feel like I might have used the right math for the green. Okay, that one was right. I haven't got a problem wrong in a while. I love math ones. Okay, so the probability that none are green. First is not green, second is not green, third is not green. That one looks right. So that's got to be right. Because that's going to be none are green. That looked right. Okay. The probability that the probability of the third one being the first blue. So not blue, not blue, blue. I think we did that one right. So blue is, unless we typed it wrong to the calculator. No. Not blue, not blue, blue. That's right. All three are yellow. All three are yellow. That's right. Is this one wrong? Because, ooh, what's wrong with this? The probability of the third one being the first blue one. Okay. Blue has a 10% probability. The third one being the first blue one. So it's literally, it's not blue times not blue times blue. Why was I doing 1%? I did it twice. So that was, Brian doesn't know how to enter 10%. I was entering 0.01%. I was entering, if you look at the original thing, as long as I multiplied it right, which it just usually comes down to enter it into the calculator wrong. I'd have to rewind time a lot to show you, but I did everything right and I wrote it right. It was the answer to the question was 0.9 times 0.9 times 0.1, but I did 0.01 if you looked at my calculator. I was like, why did I do wrong? I double checked everything while I was doing this. 0.9 not blue times not blue times blue, but I put that right there. I think I was trying to solve it in my head. No, and I was being like, let me work ahead on this. What other questions do people have? We've done a lot of the hardest ones. There's the bowler question. I don't think what else there is. I've done a lot of the other ones, but a lot of these are short. Like, those aren't long. Traffic checks on a section of highway suggest that 80%. Yeah, we can do that one. Let's do that one. Here we go. Let's do it. Of course I can, HCT. You're here? We got it. Oh, when it copies it over here now, it does it in bold. Tragic. On a certain highway. Okay. 1:09:33. Okay, if we have time left, can we do the blood? Yeah, let's do the blood pressure one real quick. So this one right here, traffic checks on a certain part of the highway would suggest that speeding occurs 65% of the time. The multiplication rule might suggest that there's a 42% chance that two vehicles are speeding in a row. Anyone ever get on Alcoa? So when you think about this, I think we're doing blood pressure next. You got it. So if you get on Alcoa and the person ahead of you is going 10 miles per hour, you cannot go speeding if it's jammed up. So each car is not independent of other cars. So because cars driving are not independent, you can't simply do the multiplication right here to find out one car is speeding another car. I actually saw someone get pulled over today. Sorry for them, but they were speeding. Don't speed. Drive carefully. So it would be these are not independent. One car's speed is completely not independent of another car's speed. Okay. Let's do the blood pressure question. The probabilities that an adult male has high blood pressure. 133. Okay. The probability that an adult male has high blood pressure, laptop not. Yeah, sure. Might be one of our last ones here. So the probability someone has both conditions. Well, I think the table just gives that, right? So the probability of both conditions is going to be simply to go in here, and you would have to have high and high. And so that's going to be 14%, the probability of having both conditions. So 14%. The probability that a man has high blood pressure is what? So that's just the probability of high blood pressure. And that would have to be this right here because you're just going down the high blood pressure. So you're going to add those and get 26%. It's either this or this. Don't look at the okay, the cholesterol here.
It doesn't matter.
Doesn't matter. 26%. The probability that a man with high blood pressure has high cholesterol. So now we're only looking at the men with high blood pressure, and we want to know if they have high cholesterol. So that becomes this over the total. So it's going to be this divided by this right here, which is the total. So there are 26% of the men total and 14% of those. So that is going to be, gosh, I can almost see that in my head. It's going to be, it's right over 1/2. So it's like 0.56 or so. Just taking a guess. 0.54. So that right there, of the men with high blood pressure, what percent have high cholesterol? So there's 26%, and of the 26%, 14%. So you just do 14 over the 26. Those are the numbers right there. Okay. 3 decimals. The probability that a man has high blood pressure if it's known he has high cholesterol. Notice how they've changed the wording here to say it's known he has high cholesterol. So that would mean you know they have high cholesterol, which would mean this. So there's a total here of 39, and the probability of high blood pressure would be the 14. So that's the 14% out of the 39%. And that's going to be, each of those is like a 2.5. Let's see here, 44% or so. Oh, I'm way off today. What is wrong? Come on, Brian. Get it with it. Go with it, man. Get your head in the game. Get your head in the game. Okay. And to 3 decimals. We should be right. Good. I was worried I'd get it wrong or something. I was like, come on, you can't get things wrong. I'm mad when I get sad when the numbers disagree. Okay. So let's go back here. Let's find that laptop. Oh, is this it right here? Is this the laptop? Is this the one, Joshua? Is this the question? Suppose that 40... We'll do this one. If it's not, we'll do the other one. So we'll just do this one here. Oh, it is it. Okay. Might be the last question of the day. And there are a lot of other questions I've done in previous videos. So check it out. Chapter 12 quiz. Suppose that 42% of families, laptop and tablet or whatever, desktop. Okay, so when you think about owning a laptop, does anyone here own a laptop and a tablet? Just write capital yes in the chat if you do. Does anyone here own a laptop and a tablet? Like you have a laptop and a tablet? Does anyone here? I do. Oh, I do because I think sometimes the more devices yours transit, it's not quite what they're going for, but I do. I have an iPad and I have a laptop. Got a desktop. So much. I think sometimes it's funny when you look at memes and stuff. It's like sometimes the more screens you have, it's like the more work you have to do. It's like sometimes the smaller the screen, like CEOs might just have like a phone or a Palm Pilot or something back in the day. But now I've got like 4 screens, so I'm juggling like chat and streaming and notes and questions. I'm doing 4 things at one time. Talk about multitasking. So what we're pointing out for this question is someone can own both. So owning one is not of what of the other. Use a word on the screen. Owning one is not what of the other. Since you can own both, owning one, look at the screen, try to find the word I'm thinking of. Owning one is not what of the other. Since you could own both a laptop and a tablet, they are not what of each other. They're not mutually exclusive. And since they're not mutually exclusive, we cannot simply add them. So think about this. 40% of people own a cat and 70% of people own a dog. What do you notice when you add together 40 and 70? You get 110%. Well, so why is it the case that you get over 100%? It's because people own a cat and a dog. So you can't add together things easily, right? Right there, Joshua sees it. You can't add together things easily that are not mutually exclusive. So because these are not mutually exclusive, and maybe I might do one quick tougher problem. I'm going to remove that one. Since they're not mutually exclusive, you simply can't add them. If a family owned, it can influence, not influence. They're not disjoint, which is the same thing. So we can't just do the addition rule because they're not mutually exclusive. Yeah. That's got it. We've done a lot of these. And a lot of these are sometimes the homework problems. Law of large number. Probability of a red t-shirt. 6, 7. Seriously, Pearson? What are you doing to me? And 3, 16. So 16. And should be able to do this in my head. Oh, come on. Come on, brain. So I think it's got it. I'm trying to do it in my head. Not black. Really? Give me back my black t-shirt. So an 8th is that, and 18.75, 81.25. Did I do it right? Man, those were not nice numbers. Favorite song, we got 6. I thought they were going to go 6, 7 again. So there's 16 songs. Of course, 16. They love that number. The probability of random song is a rap song, 2 rap songs. That's 1/8. And it's not country. Half the songs are country, so half the songs are not country. And we did that one. That one was done the homework. Very similar questions right there, homework. We did that one. That one's like, those are homework too. And, oh, this one's not bad either. We'll put quick questions in here. Speedrunning questions. Do people like when I speedrun questions? I don't know. Sometimes I'm just like, let me just do a few of these like real quick right here. So a student figures he has 12% chance of getting out of class late. If he gets out of class late, there's 37% chance he misses the train. So he knows the probability, like I get out 12% of the time late. So within that, if I were to miss the train or if I were to get out late, I'd miss the train 37% of the time. Multiply the two probabilities and get the probability of them both occurring, because in round to 3 decimals, we would lose if we didn't do that. So it's just a probability this occurs and then this occurs. And it literally tells you if this occurs, the probability this will occur next is this. So if this occurs and then this occurs, 12% times 37%. So that's got that one. Nervous kicker makes 81% of their field goal attempts. If he makes his first attempt, it goes to 90%. What's the probability he makes both attempts? So they make the first, and then the probability they make the second is this. It's literally giving you the new probability. So 81 times 0.90, and there's the new probability right there. So just multiply. This is giving you the probability, saying if this happens, the probability of this is this. And we've done a lot of them. Okay. Funding. Okay, wait. The additional rule might suggest that 49% of the residents have a paved driveway or a fireplace. You can have both. They're not disjoint. So they're not disjoint. You can have both. So you would do that. We've done over half of, we've done a lot. If you look at, I know I sped through those, but those are like the simple ones. And we did a lot of those in the homework. Do people feel good about this? How are people feeling about this? I'm going to go on a walk. It won't generate exactly, approximately, and you wouldn't be able to predict. So it would generate 50-50 approximately, and you wouldn't be able to predict. Points. So what this says is that when you flip a coin, in the long run, it's going to be about 50-50, and it doesn't mean infinite. And then you can't predict what's going to happen when you flip a coin. That's what random means. Seeing what random means, then in the long run, a fair die will produce roughly equal amounts. That sounds about right. But for each value we don't know, they're about equally likely. Yeah. Kind of the law of large numbers entailed in it. After rolling doubles on a pair of dice, your friend says, I cannot get doubles 4 times in a row. That's the gambler's fallacy. That's the law of averages. So we just look for things like fallacy, law of averages when I look for an answer. There's no law of averages right there. Yeah. There's no law of averages. It's not like I'm due for a win. So we only have 4. 2. We did everything but 6 questions. Everything but 6 questions. And I know I've done the bowler, and I know I've done blood type. Those exist. And these are a lot like the homework. So with that, we're going to head on out. I'm going to take a break. I'm going to walk around. Enjoy the nice weather. Bye for now, everyone. Bye.